All right, today we're going to do something really cool. We're going to connect two worlds that might seem totally separate. The abstract world of AI algorithms and the nuts and bolts physics of drone engineering. We're really on a mission here to figure out not just how an algorithm learns to think, but how the machine it's inside, the drone, can actually learn to survive.
And really, that's the perfect way to think about it. The AI is the brain, right? It's making all the decisions, spotting the patterns. And the drone, well, that's the body. It's the thing that has to actually carry out those decisions in the real world, which, as we all know, is messy and totally unpredictable. So yeah, let's follow that whole journey, from brain to body.
And that really brings us to the big question, the one that ties this whole thing together. See, it's not enough to just build the smartest AI or the fastest drone. Nope. The real challenge is building a single system where that brain and that body work together to be resilient, to not fall apart when things go wrong.
Okay, so let's start with the brain part of this equation. First things first, we've got to get the language right. You hear these terms thrown around all the time: AI, machine learning, deep learning, and they are not the same thing. The best way I found to think about them is like one of those Russian nested dolls, one inside the other.
So the biggest doll, the one on the outside that holds everything else, that's artificial intelligence, or AI. This is the big granddaddy concept of it all. The whole goal is just to get a machine to act human-like, to mimic our intelligence in any way it can. And that includes everything, even really simple, old-school if-then programs from way back when.
Okay, so you open up that big AI doll, and what do you find inside? The next one, machine learning, or ML. Now, this is where things start to get really interesting. Because with ML, we stop telling the computer exactly what to do. We stop programming every single little rule. Instead, we just throw a mountain of data at it and let the algorithms find the patterns all by themselves. It's literally learning from experience. And then, finally, you open up the machine learning doll, and you get to the very center, the innermost one. That's deep learning. This is a super powerful type of machine learning that uses these really complex layered things called artificial neural networks. I mean, these networks are the secret sauce behind solving some of the hardest problems out there, like your phone understanding what you're saying or identifying your friends in a photo.
So, how does one of these networks actually, think? Well, it all starts at the input layer. That's where the raw data comes in. Could be pixels from an image, readings from a sensor, whatever. That data then gets passed into the hidden layers. And this is the real engine room. This is where all the heavy lifting happens and the complex patterns get sorted out. And finally, after all that churning, the output layer gives you the final answer, a prediction, a classification, you name it. And the learning part? It's basically just tweaking the connections between all those layers, kind of like adjusting a bunch of little knobs on a series of pipes until the flow of information gives you exactly the right result.
Okay, so we've got the basic structure down, but how do we actually teach these things? Well, that brings us to the most important part of the whole process: training and testing. And to make this super clear, we're going to use a really classic and honestly pretty powerful example. So there are basically two main ways these models learn. The first is called supervised learning. Think of this like studying with flashcards that already have the answers on the back. You give the model a bunch of data that's already labeled, a million pictures of cats, and every single one is tagged, "This is a cat." The other way is unsupervised learning. This is more like being dropped in a new city with no map and being told to figure out the neighborhoods. You just give the model a ton of raw, messy, unlabeled data, and it has to find the patterns in the structure all by itself.
So, to see how this kind of logic really works, let's dig into a famous supervised learning problem trying to predict who survived the sinking of the Titanic. You can build a pretty simple model called a decision tree that just follows the data step by step. And the very first question it asks, well, it's incredibly telling. Get this. The model crunched all the numbers, and the single most important factor it found? It wasn't how much money you had or what class you were in. It was your gender. If you were a woman on the Titanic, your chance of survival, right off the bat, was 73%. Just that one piece of information had massive predictive power.
But if you were male, the model sent you down a totally different path. The next thing it looked at was your age. And for any man or boy older than about 9.5, the survival rate just plummeted, all the way down to 17%.
And it gets even more granular from there. The model looked at the younger boys and asked, okay, how big was their family on the ship? If a boy under 9.5 had 3 or more siblings or family members with him, his chance of survival dropped to a staggering 2%. I mean, it's absolutely chilling to think about, but it's a perfect illustration of how these models can follow a clear, step-by-step logical path.
But this leads us straight into a huge trap in machine learning. It's called overfitting. You can build a model that looks absolutely perfect. It gets a 100% score on the data you trained it on, but then you show it something new from the real world and it just completely falls apart. It's like a student who memorizes the answers to the practice test but doesn't actually understand the concepts. The model didn't learn the general rule, it just memorized every single little detail of the training data, including all the weird random noise.
So how do we stop that from happening? How do we get a truly honest look at how well our model is going to do in the wild? Well, we use a clever technique called K-fold cross-validation. Here's how it works. You take all your data and you chop it up into, let's say, 10 equal chunks, or folds. Then you train your model on 9 of those chunks and you test it on the one you left out. Then you do it again, but you pick a different chunk to be the test set. You keep rotating and repeating this until every single chunk has been the test set exactly once. It's a way more robust, more honest way to see how your model will actually perform.
You know, this whole idea of building a model that doesn't just memorize, but can actually handle new stuff it's never seen before, that's really a form of resilience, right? It's software resilience. And that concept, right there, is the perfect bridge that's going to take us from the abstract world of code and algorithms to the very real world of physical machines.
Okay, look at this. This really makes you think about what best even means. You've got 2 models. Model number 5 looks great on the surface. It has the highest overall accuracy at 78%, but look at its false negative rate, 12%. Now, if this is a model for cancer screening, that means it's telling 12% of sick people that they're healthy. That is a catastrophic mistake. Now look at model number 1. Its overall accuracy is lower, only 68%, but its false negative rate is just 1%. So, which one do you pick? It's a no-brainer, right? You don't always pick the model that's right the most often. You pick the one that avoids the most dangerous, most devastating kind of wrong.
And that exact same thinking applies 100% when you're engineering a physical thing, like a drone. The question isn't just how well does it perform on a good day. The real question is, how do you design it to survive when things inevitably, and they will, go wrong?
So there's actually a formal framework for thinking about this, sometimes called the 5 R's. It's a great little ladder of concepts. It all starts with robustness, just the raw ability to take a hit without breaking. That then allows for redundancy, having spare parts, backup systems. But backups are useless if you can't use them, which requires resourcefulness, the ability to actually switch to your backup when you need it. And you got to do it fast, which is rapidity. When you put all 4 of those together, robustness, redundancy, resourcefulness, and rapidity, what you get as the final outcome is true system resilience. And this is a perfect, simple example of that trade-off in action. On the one hand, you've got a quadrotor. 4 rotors, super efficient. But what happens if one motor fails? It's going down. That's a single point of failure. Now look at the hexacopter. 6 rotors. It has built-in redundancy. It can lose an entire motor and just keep flying. Now, it's not as efficient, but it is way more robust. It's a classic engineering trade-off.
And you know what? This idea is not new at all. Check out this absolutely brilliant piece of old-school engineering, a mechanical truck counter. It's just a spring-loaded platform on a road, and it was physically built so that only the weight of a fully loaded truck was heavy enough to push it down and trigger the counter. Lighter cars and empty trucks just rolled right over it. It's a physical filter. It's designed to separate the signal from the noise, a perfect example of robustness built with clever mechanics instead of a single line of code.
Okay, so this brings us full circle. We've talked about the AI brain, we've talked about the drone body, and now we're bringing them back together to face one last, really critical choice you have to make when you're designing these things.
And this quote really says it all. In any complex system, trying to be perfect is a fool's game. It's just impossible. Your model will see something it doesn't understand. Your hardware will have a part that fails. So the whole goal has to shift. You stop trying to just maximize performance, and instead you focus on maximizing the ability to handle failure gracefully. And maybe, just maybe, even learn from it.
So this leaves us with a really deep question, one that's not just about engineering, but maybe even about ethics. When you're the one designing these systems, where do you draw that line? Is it better to push for the absolute peak performance from the AI, make the brain as smart as possible, or is it better to guarantee the fail-safe, rock-solid resilience of the machine it controls, making sure the body can survive even when its brain makes a mistake? That choice, that trade-off, is really at the heart of everything we're building for our automated future.